Welcome back. All right. I'm going to cover gradient descent with momentum. All right. So gradient descent is great, and I mentioned it has a lot of applications to machine learning and control theory. Some time to time, if not all, I see that, like many other researchers, gradient descent can cause oscillations when functions curve steeply. And because of this, by the way, this is the standard gradient descent that I covered in the previous video called gradient descent. You can watch that video first if you haven't watched. Basically, gradient descent with the addition of momentum term can accelerate gradient descent and suppresses such potential oscillations. Especially, this is important that you can get smoother and slightly faster sometimes estimates. And here is a great paper on momentum term. If you want to find details, you can read this paper published long time ago. And this is another paper published, if my memory is correct, 2016, an overview of a bunch of gradient descent types, including Nesterov, Adam, and all these fancy ones. Maybe later we can dive into those, but this regression and control lecture series has a specific objective that touches both machine learning and control theory in some spatial sense that will be useful for control. This video will be more about least squares and how we find iteratively least square solution using gradient descent with momentum. To make the long story short, I will start with the general form. You have a function, cost function, scalar valued cost function that you would like to minimize, that you would like to find the parameters W iteratively. This is the standard gradient descent, and with momentum, it looks like this. Basically, you have another player here that you need to update, mu k plus 1 equals to its previous value of mu. Actually, in this paper, it says that mu should be chosen close to 0.9. It's a great paper, the great author, and many other researchers suggesting that the gamma should be chosen like this, like that. I will give precise definition, if you remember this unit circle type of a definition, how they need to be chosen such that guaranteed convergence to local minima is happening. All right, so in this with momentum case, you put the gradient here that you would like to minimize, and you update the parameters according to this. You need to choose alpha for the gradient term and gamma for the momentum term, and this is how the equation changes. This is the standard gradient descent, this is the gradient descent with momentum. And we're gonna understand the underlying theory, as well as you are going to see a Matlab example with code. Let's proceed. I am revisiting our initial friend, which is the line model, right? If you remember from the previous videos, this video, if you haven't watched, please watch this video first. To start slow, again, we are soon going to skyrocket, but you need to understand these initial videos precisely so that everything will be crystal clear. We have some data points and data points. For example, this is the ith data point, dependent. This is the independent variable ith. Let's say this is I plus 1, so on and so forth. So we have n of them. We would like to estimate, we would like to fit to these data a line model. We have some unknown vector w, w0, w1 multiplied by 1 and x. And on this video, we basically formulated, this is the omega matrix, and this is the y. And we minimize this cost function that you see that uses these elements. And the gradient of that cost function was this. Again, all coming from this video. But I am going to use them now in the current video as well. Again, these lecture series, all these videos progresses based on the knowledge you obtain from the previous video. So we just go like a lecture. That's why I call it a lecture. All right, so you already know the analytical solution from this video, but I believe on the gradient descent video, the previous video, I give the motivation behind the iterative solution for applications to large data sets if the data set changes in time, and later we're gonna connect it with control theory. All right, so I am taking this generic equation. I am going to insert the gradient with this gradient. Once you do that, you obtain this equation. You can rewrite things like mu depending on w and y, and this is the other one. I have two different equations. These are discrete time equations. I would like to write them compactly like this. So we have this A matrix again, right? Gamma I here, this guy here, minus identity here and identity here. For them to be compatible, I need to include these identities multiplied by this state. This is the input, this is the B matrix. Now, we are dealing with a discrete time difference system, and the natural question is, if you look at here, how you should choose gamma and alpha. You always need to choose them theoretically so that your convergence is guaranteed. If you remember this video, if you haven't watched, this is a little bit long but very useful video in understanding the stability of discrete time systems, and right now you are dealing with a discrete time system. The eigenvalues of A must remain in the unit circle. So A needs to be sure. If all the eigenvalues, not one, all the eigenvalues of A is inside the unit circle, then we call it A is sure, then the convergence is guaranteed. So if you look at this A matrix, right, you need to tune gamma and alpha such that if all the eigenvalues are inside the unit circle. And this unit circle, let me draw it here, right, real axis, imaginary axis. This is 1, minus 1, j, imaginary minus j. These, basically I am marking these points. For example, if you have one eigenvalue and if it is between minus n and 1, then you are on this region, you are inside the unit circle. If you have a complex eigenvalue, you need to look at its basically absolute value, right? This is the circle equation, and if this complex eigenvalue, basically sigma to the power of 2, p to the power of 2 square root is less than 1, then it is guaranteed to stay inside this unit circle. So you need to do this for all eigenvalues by choosing gamma and alpha. If your eigenvalues are outside the unit circle, make them smaller. Now, if A is sure, meaning that your eigenvalues are inside the unit circle, then Vk will converge to its analytical solution. What is the analytical solution? This is the solution that we established in this video, meaning that your convergence is guaranteed, very precise, very mathematically precise. So to see this, we need to find the equilibrium point. Equilibrium point is the point motion stops, meaning that the next value of mu k and wk equals their previous values for all k. So once you do this, basically if you solve, I am now looking at this equation, I replace this with this since motion needs to stop. I am looking at the first row. From the first row, I am going to, let's look at the second row, my mistake. From the second row, you are going to obtain wk equals to minus mu multiplied by w and 0. Basically, you have this equation. If you solve this, these will cancel out and mu will be 0, meaning that as k goes to infinity, the equilibrium of this momentum part, mu equals to 0. Now I am looking at the first equation. Mu equals to gamma mu, but mu is already 0, right? It is going to 0, so I am going to make them 0. This term multiplied by w and this term multiplied by y. So these remains. If you solve this for w, you are going to get basic the analytical solution, W will converge to its analytical solution. Okay, I will keep it simple. Basically, choose alpha and gamma such that eigenvalues are inside the unit circle. If you haven't watched this video, make sure all eigenvalues satisfy if real this condition, if complex this condition, then your gradient descent with momentum will converge, will make W to converge its analytical solution as k goes to infinity. Perfect. Now it is time for examples. First, as compared to previous videos, I increased the data points here. Instead of basically 6, I am using now 10. Because I am trying to construct an example where gradient descent may oscillate, right? Again, you may not need always gradient descent with momentum. Gradient descent nicely works, but there are cases if you see that you have huge oscillations that you are going to see from this video, then you may replace it with gradient descent with momentum. It is faster, less oscillations, smoother. It is a very nice approach, basically. There are a lot of gradient descent approaches. I really like gradient descent with momentum. Nestero is also popular, also pretty similar to gradient descent with momentum. Maybe I can cover in a different video, but as applications to control theory, I really like gradient descent with momentum. To make the long story short, right, I am using standard gradient descent in finding this solution. This is without the momentum term. I of course first do the eigenvalue check. Eigenvalues are inside the unit circle. Perfect, then I can proceed. Here, since I am using gradient descent without momentum, I only have one tuning parameter, alpha. And as I mentioned, I choose it to satisfy this eigenvalue condition. This is the iterative solution. This is for plotting purposes. Similar to the videos that I posted previously on the previous videos, you can stop it, take snapshot, code it yourself. If you have any questions, leave a comment. And if you like this series, subscribe. You can suggest to your friends, turn notification on. We can go from there. Feedback is very valuable. And here is how W's converge. In the previous example, in the example in the previous video, we had a nice convergence, and here we have oscillations. So now exact solution to W1 was 0.34. This converges to 0.3433. We have oscillations, but convergence is not bad. And convergence is indeed guaranteed, right? We are selecting eigenvalues from the unit circle. And exact solution for W2 was this. We converge to this. After a while, once you fit, it is a nice fit. Now, why you may ask, well, we converge. Why do we care about these oscillations? Two reasons. One, from a basically machine learning standpoint, if let's say you stop the algorithm here and you use this value, or let's say you stop the algorithm, you use this value. Basically, these are oscillating around the true points, and if you use this video, then your line fit may be wrong. From a control theoretic standpoint, later when we extend this to the usage of control theory, in this dynamical system response, we don't like oscillations. Like you are controlling an airplane, you have passengers, your airplane oscillates. Then passengers get motion sick. You don't want that. Anyway, we run this code for 75 iterations, and this is the plot using the estimated value at the 75th iteration. It is a nice fit. Now, I am now implementing gradient descent with momentum. Same data set, same omega. I now have additional player. Alpha was 0.8. I needed to play with these numbers in order to have eigenvalues inside the unit circle. Okay, so I decreased this. I just would like to pay more attention to the gamma 0.5 since it smoothens the performance. After doing eigenvalue check, like in here, this is the basically mu iteration and W iteration. This is the, in Matlab code, this is like mu k plus 1 equals to the previous values here. Likewise, this is wk plus 1 equals to wk minus mu. Then the same process for data visualization. As you see here, you have two observations. basically you converge very smoothly, much smoothly, no weird jumps. And if you look at here on a ballpark, not a big difference, but these data that converged at after 75 iterations are more close to the exact solution. Although this is really tiny, but it is a slightly fast convergence, but much more oscillations. Again, the most important feature of the gradient descent with momentum is removing oscillations, and also it can provide faster convergence. And here is the fit, basically very nice fit. And I hope you like this video. Again, you can subscribe, turn notifications on, we can go from there. As always, your feedback is important, really. So if you have any questions, if you want me to cover some new topics related with regression and control, please let me know. Take care.